Hi everyone. We've been looking at a lot of patterns lately, specifically with numbers and just kind of seeing what term comes next. And what I wanted to do in this video is to give you a concrete way to describe a sequence and to find the next term of a sequence. So our objective for today is to be able to write an explicit formula to describe the general term of a sequence. And when I say general term, I mean this formula will calculate any term of a sequence. I think the best way to jump into this is just to look at some examples and find some patterns. And then we'll kind of backtrack to like the formula part. So we're looking at a couple different sequences in this video. The first one we're going to look at is 4, 7, 10, 13, 16, 19. I want you to take a second and think about what pattern you would follow to get from one term to the next. So from 4 to 7, but the pattern has to be consistent. So 7 to 10, so on and so forth. See what you think, write something down. If you need to pause the video, go ahead and do that. So from 4 to 7, I see, if I'm thinking addition, I'd have to add 3, and that trend will hold true for the entire sequence. So from 10 to 13, you also have to add 3. From 16 to 19, you also have to add 3. So this one had a difference that you would add. Sometimes the pattern is an addition, though. It could be subtraction, multiplication, division. It could be like a pattern. It could be a lot of things. In our particular context, we're going to talk about ones with a specific trend, and this is a trend of addition. And we actually call this an arithmetic sequence. So an arithmetic sequence here is a sequence with a constant difference. Constant, or I should say sum or difference. Okay, it's called arithmetic because what does that word also look like? Arithmetic. So there's arithmetic between each next term of the sequence. That word constant is extremely important. What that means is you're adding 3 each time. You're not like adding 3, then 4, then 5, so on and so forth. Okay, so the first difference is 3, so this is arithmetic. We want to work towards writing a formula for the general term of a sequence. And I want you to start comparing sequences to functions a little bit. So what I mean by that is, and I'm actually going to literally write this as a function, although I know it's not. Let's call x the order of which the term appears in the sequence. So like this is term 1, term 2, term 3, term 4, term 5, term 6. So x is the order of the element in the sequence. And let's call y like the output would be like what the term of the sequence is. So 4, 7, 10, 13, 16, 19. Now, every time you look at a sequence, you might not compare it to a function, but I think this is an easy context to understand. So what kind of function would it be if you were adding a constant difference or sum to each term? So you're going up by 1 on the x's, you're going up by 3 on the y's. This would actually be a linear function. Okay, so to write a formula for it, it can actually model the fact that it's linear. So when I say it's linear, it's got like a constant slope, right? Like you'd rise 3 on the y, you'd run 1 on the x, so slope would be 3. So if you think about what a linear function looks like, the explicit formula to calculate the terms of the sequence is going to look very similar. So the function comparison would be y equals mx plus b, where m is your slope and b is your y-intercept. Maybe you wouldn't call this y, maybe you'd call it f of x. That's up to you. Okay, now while we call a function f of x, we do not call a sequence f of x. We call a sequence like a sub n, where a is the name of the sequence, and n is what we call the index. Now all the index is it tells you the position of that sequence element. So when I say position, I mean like 4 is in position 1, 7 is in position 2, right? It's kind of like your x value of the function. So this n, again, tells you what order your term is in. So if I said like A1, right, it would be the first term. If I said A2, it would be the second term. Anyways, now you're going to write an explicit formula to generate any of these terms. And when I say explicit formula, it's kind of like writing a function. So our function is in term of n instead of x because it's a sub n. But we know this is linear, so it'll model a similar format here. So our slope to get from 1, well, you're rising 3, running 1, so our slope is 3. But instead of 3 times x, it's 3 times n. Okay, if I just did a sub n equals 3 times n, well, what would happen then, right? These are not x's anymore. These are n's, and these are like my a-n's. So if I just did 3 times n, well, 3 times 1 would give me 3, but that's not what I have here. 3 times 2 would give me 6, but that's not what I have here. 3 times 3 would give me 9. That's not what I have here. So what would I need to alter about 3 times n to get the actual sequence defined? Well, 3 times 2, for example, gives me 6, but I have 7, so I'd have to add 1 to that. You just want to check that and make sure that works for everything. So term 6, 3 times 6 is 18. If I add 1, I'll get 19. So that would be the explicit formula to define the sequence. So there's 2 ways you can look at this. You can model it off a linear function and then just kind of interpret it as a slope, or you can think about it more generally and not even compare it to this function over here. So I'm going to even erase it. Let's just say you were kind of looking at this, you were just looking at patterns. You could totally think about this. So really what you're doing to get from one term to the next is adding an increasing amount of 3's, right? So from 4 to 7, you have to add 1 3. But to get from like 4 to, I don't know, 16, how many 3's would you have to add to 4? You'd have to add 1 3, 2 3's, 3 3's, 4 3's. Okay. So you're adding an increasing amount of 3, so 3 needs to be multiplied by some number. That number is what term it is, it's our n, but I'm adding an increasing amount of 3's, which is really multiplication there. That's why I do 3 times n. But if I just leave it as 3 times n, that doesn't give me the sequence, right? That would give me the sequence. So if an were 3n, you don't have to write this down, but I would get the sequence 3, 6, 9, and that's not what I want. So this sequence is like shifted or transformed. If you think about it as a transformation, you can say up 1, right? So if there's a graph, it'd be shifted up 1, but the sequence itself is shifted plus 1 from that sequence. So sometimes what I tell students is if you get this far, and you know it's 3n, well, write out that sequence. So it's 3, 6, 9, 12, and then compare it to the original sequence if you get stuck. So how does 3, 6, 9, 12 compare to this? Oh, I have to add 1 to each number, and that's where this plus 1 comes from. So that's a way to think about it. Okay, let's try number 2. Number 2 is slightly different from number 1, so I want you to just go ahead and look at patterns. What do you see? You can pause the video. Okay, so it's kind of weird because it's alternating positive, negative. So if I added something, that wouldn't accommodate for positive, negative, so I have to be multiplying by something. So to get from 1 to negative 3, you're multiplying by negative 3. But does that pattern work for the rest of it? If I multiply by negative 3, will I get 9? Yes, I will, because the negative times the negative is a positive. So the pattern is generally you're multiplying each term by negative 3. So this is no longer an arithmetic sequence because an arithmetic sequence has a constant sum or difference. So what defines a geometric sequence is that you're multiplying by a constant amount or a fixed amount. Okay, so adding constant, arithmetic, multiplying, geometric. And in order to look at a geometric, we can also kind of compare it to a function. So if we are multiplying by an increasing amount of numbers, really this is kind of going to model an exponential function, right? So an exponent means, like if I have 3 to the x, then I would be multiplying an increasing amount of 3's, right? Like 3 to the first would be 1 3, 3 squared would be 2 3's. So this function, or excuse me, this sequence models this similar function, except I'm not multiplying an increasing amount of 3's, I'm multiplying an increasing amount of negative 3's. So it's kind of like the function negative 3 to the x. Now, I'm going to use the method I talked about just before in arithmetic, and let's say I call this an, so no longer x, but it's n. Would that give me the sequence that I want here? So if I plug in term 1, right? So term 1 is actually 1, so that's kind of confusing, but if I plug in 1 for n, then I get negative 3. And if I plug in 2, so term 2 is negative 3 for n, I get 9. If I plug in 3, so this is term 3, so negative 3 to the third is going to be negative 27. Is that the function I want? No, it's not, because if I plug in 1, I should get 1, right? But I'm actually getting negative 3. So it's kind of like negative 3 to the n, but it has, again, been shifted. So the question becomes, like, how do I adjust this to match what I have here? I want you to think about that. Pause the video and see if you can come up with the answer. Although I asked you to think about how to change this, I do want to talk through it because this can be challenging. So what I think about in my head is term 1. Term 1, if I plug in 1, did not give me what I wanted to, right? Like term 1 in this explicit formula would have been negative 3. So how would I, change this n to make my term 1 a 1? So So the question is, what exponent do I have to raise this to be 1? So the answer to that is anything to the 0 power is 1. So if I make the exponent a 0, then I'll get the first term I want. Okay? So that's kind of like my thought process, but I still don't know how to adjust this function. So remember, if I write this as a function, my n would be like 1, 2, 3, 4, would be the order of the term, and my an would be 1, -3, 9, -27. Okay, so n is still going to be 1 when I plug it in, but I need to adjust this to make it 0 when I plug in 1. In order to do that, I have to subtract 1 from the n. Okay, so if I do this, you can test it now. So if n is 1, I have -3 to the 1 minus 1, which will give me the 0 I want in the exponent. So then my term 1 would be 1. If I plug in term 2, or if I plug in 2 because I want to find term 2, it's going to give you -3 to the 2 minus 1. 2 minus 1 is just -3 to the first, which gives you -3. And now term 2 has given me the term I wanted to. Okay, so you can compare arithmetic to a linear equation. You can compare geometric to exponential. The point is, though, you're going to have to transform the parent function, right? Let's not call that a parent function anymore. It's like the parent sequence, right? You have to compare what you think it is to the actual sequence and make adjustments from there. This is how I like to introduce these sequences because you can compare it to background knowledge on functions and you can analyze patterns a little bit more. But there are definitive formulas you can use to find the explicit formula for an arithmetic and a geometric sequence. I don't recommend memorizing these, but it may be helpful to you. So for an arithmetic sequence, the formula to find the explicit formula, I know that's really confusing to say, is you take the first term, which we call A1, and you add it to n minus 1. So remember, A1 is the first term, n is the position that term is in. So like position 1, position 2, where is it in the sequence? And if you plug in our information here, you would wind up getting the same thing. So if I use that formula here, I'd have an equals A1 plus n minus 1. You get the same formula I came up with. So why don't you go ahead and plug that in and try that and figure out if you get the same thing on your own. For geometric, the general formula is A1 times r to the n minus 1. Okay, where A1 is the first term, r is like the common multiplied factor, so like -3. N is still the position of that term. So r we call the common ratio. I should actually define that. R is common ratio. It's like what each number is getting multiplied to get the next term. So -3 is our common ratio. So this is a more concrete way to come up with the formulas without just like thinking through it. So again, I want you to do that for, oops, this should have been up here, my bad. I want you to do that on your own. So use these general formulas. So r to the n minus 1. Plug in the information and see if you get the exact same formula we came up with. So these were the formulas we came up with. Okay, also on your own, I want you to take a look at this question. I want you to write a list of steps so you can kind of conceptualize what we were doing. And then if you want to try some more practice problems, they're here for you. I know that was a lot of information, but please come with questions.